think Chuck is also easier for people who don't have a lot of programming experience.
Yes, it's much easier to learn than
which is great for I guess that makes it perfect for 228.
It's a great thing for teaching.
Yeah.
It really is.
I think Faust Live, they just came out with a new version of Faust Live, which is a rapid sort of reiteration. Will be a good stand, and also for the super collider competitor, at least in the realm of interpretive language, it's quasi-interpretive.
Well, another thing to mention is that there's a Faust to super collider script, and there's a Faust to Chuck script. So you can, do your signal processing in Faust, and then create a SynthDev for super collider and a chug-in for Chuck.
Yeah.
Thanks to Spencer.
So this is all autocorrelation, pitch tracking. What's the difference between this and FFT if you're trying to do an FFT and then observe that and try and figure out what the pitches were?
Doing it in the frequency domain can be faster. You can still do autocorrelation in the frequency domain, but yeah, you get some algorithmic efficiency by doing it in the frequency domain instead of the time domain.
How, I guess visually I don't understand how you can autocorrelate an FFT with itself, because it seems like it would have the same period amount of where the spike was.
You chunk the FFT into, you take the time signal, right? And you take some number of samples, and you take an FFT of that. Then you take another chunk of samples at some later point, and you take an FFT of that. And then you can do autocorrelations on the multiple FFTs.
And the fastest way to do an autocorrelation is take the FFT and multiply it one by the conjugate of the other. So, fast convolution is the same basic thing as fast autocorrelation. So anyone who really implements a lot of long autocorrelations, it has to be over like 100 samples. In this case, you may not need that many, but you want to be using the FFT just for time domain autocorrelation because it's the fastest way to do it.
Gotcha.
In fact, the MATLAB autocore function uses an FFT-based method for calculating it.
But to be clear, this is better than what we could just guess by just looking at an FFT.
Well, in principle, the Fourier transform of the autocorrelation function is the squared magnitude FFT, right? So there's the same information. So it's just a linear transformation. It's just what do you want to look at? And so I think one of the main questions is, what does the ear look at? What does the brain look at? And the brain is more looking at the FFT peaks than it is doing autocorrelation analysis. But you have to be careful because the brain's also doing time domain analysis. So there is direct perception of periodicity, especially low frequencies, and there's processing of spectral peaks and recognizing harmonic rows of peaks in the frequency domain, especially at intermediate frequencies. And at high frequencies, only if they align can you get some time domain processing at the pitch interval, period interval. So you really have to look at perception, and your brain is trying to do the best it can, and it does things differently in different frequency ranges. So you really have to think time frequency at all times, because the brain is doing that.
I've got a couple good papers that talk about looking at different pitch detection algorithms that compare a bunch of different algorithms, if you'd like me to send that your way. There's one from a couple years ago on, I guess, looking at guitar sounds. Guitars are very popular in computer music. So there's
Guitars are very popular in computer music. I will not tweet that. That is maybe true today, but it is not true in the beginning. In the beginning, there was no such thing as a guitar. So what in the world are you saying?
In the actual beginning.
what am I saying?
Yeah, I mean, please.
Oh, there's a paper that I think you said it. I forget what it's called. There's a paper that looks at 5 pitch detection algorithms for real-time applications,
I see.
and the test signal they used is a guitar.
I see. So it's kind of become the fact that a standard test signal.
Yeah.
Or pitch detection.
Well, I wouldn't say that. I'd say it's a popular choice because so many people play guitars. There's a market for
Everybody's got
pitch detectors that work on guitars.
Right.
Also, guitars are so interesting because they have so many weird non-periodic elements to their signal, right? Every attack is basically noise initially.
Well, like flamenco people actually, use the guitar like a drum. That's always cool.
Yeah, there's a lot of cool stuff about guitars.
Perhaps that's fun.
I agree.
Voice is a hard case because it's so all over the place. Guitars at least tend to hit one pitch and stick to it.
I was thinking just because of like, I don't know, the strings, it's like visualizing the harmonics, or like, what the harmonics are gonna be and stuff like that, whereas like with voice, just depending on the vowel, they're all gonna be different. What harmonic strings and stuff. Yeah, like the ones that are brought out are all gonna be like different.
Yeah, the guitar has a fixed resonator, the voice has a variable resonator. And the resonator is modulating information content.
They even tell you that in the help file. Some vowels are still problematic. For instance, wide open mouth sound somewhere between a low-pitched short A sound as in sat and the long I sound as in fire contains enough overtone energy to confuse the algorithm.
And which one is that pitch?
That's pitch.
So if you have too much overtone energy, then you get a large secondary peak at like the octave up or something like that. Because it kind of crawls out from the, the minimum pitch, or no, it crawls out from the maximum pitch, because the maximum pitch corresponds to the shortest period. So it'll start at that lag, and then it goes crawling until it finds, a large local maximum, but it'll stop before it gets to the maximum period, which is the minimum pitch. And so then, if you have too much overtone energy, the largest peak might be a higher octave or something like that. And so, yeah, so it can depend on fundamental frequency, as we saw in the demo, and it can depend on the vowel, which gives you variable EQ that can suppress the fundamental. So that's a good reason to go to Tartini. In that situation, Tartini will do wonderfully because you're still going to have lots and lots of harmonics. They're all going to be separated by the fundamental. So if you do a histogram of the overtone spacing, you're going to get a big giant pile at F0, the fundamental.
Right.
And it's very robust, and that's why we hear it so robustly, because we're doing that in our brains.
Right. Cool.
Okay, Elliot.
So why don't we take a 5-minute break, and then we'll have the Shazam story, or at least a spectrogram or two.
Elliot, how did you do that FM bit?
That's a sine oscillator where the frequency argument is another sine oscillator.
But you don't have to put .AR, or you do? You do.
Fundamental.
Okay, but you don't. Okay.
Do you want me to show you this design?
Yeah. Well, I'm doing it over. I'll just keep fucking with it until you're done packing. I downloaded it.
Supercliner is free. Free, open source.
Yeah, I got it from the source forge. That's where I believe it was forged. Yeah. So the frequency argument, okay. But there's like usually a carrier frequency and then a modulator frequency. But how do I like?
Right, so
define a carrier?
in that example, this is the carrier, this is the modulator, right?
Yeah.
So all of this is the okay, so this is the frequency argument to that sine oscillator.
Okay.
This is saying the phase and the amplitude. Okay? So the frequency is another sine oscillator. And that sine oscillator, its frequency argument is this.
Yeah.
Which is
an
exponential
exponential
function
function
changes
going
going
from
from 1 to 1,000.
So if I don't need it to
seconds.
change, I can just put it, like 400.
You can just put in
Yeah,
400.
it'll do
Yeah.
VSTs too.
And then it has
Wait, is that true?
no phase argument. It's being multiplied by 200,
KVR
and there's an
is
offset of
so
800. Because in FM synthesis, you need that.
Amplitude to be higher.
Right. Because that increases the harmonicity.
That graph is
Yeah.
good, but I think in this case it might be easier if I do a
Spectral
spectrum
content.
where I actually can see it graph
Oh.
out like as time goes on.
I think you're out of luck.
I mean, you can get one, but there's not.
Oh, okay, that's kind of
I don't have any recommendations.
So, okay, I just thought there's like, the carrier frequency, I don't see where it's defined.
The site's
The
usually pretty
carrier
useful
frequency
just
is,
finding the ESPs and I guess I've seen
I
that
think
option, but
it's
I've never
800,
done it
right?
before.
So this 800 effectively plus the value of this sign oscillator, right?
So which
This whole thing,
argument is that?
okay, so if I get rid of this, X, right? This won't actually compile. So this is a single sign oscillator, and that thing that I cut out, this is the modulator. So all this without the sign oscillator is modulating this one. And then these other arguments, you can ignore this.
To know enough
This
stuff.
phase argument.
It would
This
probably
is
be
the-
wise to take 320. You might, you want to do both at the same time.
Right?
That's what-
So 800 is
Considering.
actually the frequency of this sign oscillator.
You're
800
busy with signal processing.
Plus,
So
what does that do?
if that's what you're trying to learn, that's the way to do it. I said, if you take both, you'll be very busy with signal processing stuff. If that's what you're trying to learn, that's what
You can draw on that, that's fine.
264 is harder than
right?
either.
So we have a sign oscillator that
So,
goes from
yeah, you could probably say them both at the same time, but,
use a mole factor. We do mole
which
factor
course you
two,
guys have?
and
Oh,
right?
Schaefer bowl right now, anyway.
Is that the application?
It won't say that.
Oh, it's DC offset. Cool, so yeah, so that makes perfect sense.
Right,
That's-
so that
that's the
800
carrier frequency is what you would,
Exactly.
you would start with to modulate the frequency.
Right.
Awesome. Oh, this is really cool. I'm so into it.
Do you remember the name of that paper offhand?
What is that?
It's on
That's
my
like
computer.
so good.
Let me go.
So great.
You guys have like a Piazza or listserv or something?
Yep, yeah.
I'll send Chet an email with all the links, and then he can send it to the.
Yeah.
Yes and yes.